Hi, everyone. Just a quick check in the back. You can hear me okay? Perfect. So thank you for attending this talk about self-learning caches. My name is Irfan Ahmed. I am a co-founder for a new company called Cache Physics. Prior to this, I worked at a venture-funded company called Cloud Physics for 5 years. Spent 9 years at VMware working on the ESX kernel as well as distributed resource management, so large-scale storage management, performance modeling of storage done completely automatically to provide lights-out data center management to large-scale customers. Started my career at Transmeta and come from the University of Waterloo, so hopefully there's some fellow Canadians. Almost always there's somebody that raises their hand, so I'm hoping there is. The company that I'm going to be talking about is focused on, seems like there's an echo, is focused on data path monitoring and modeling, and then using a very X-ray-like, MRI-like understanding of the data infrastructure to then provide a whole bunch of advantages that we'll talk about. But before all that, my previous company, which is where the ideas that we're working on now really arose, this was our automation journey, right? We had these very large-scale data ingest systems and data analysis systems. Some of them were real-time, some of them were batch. And 6 years ago when we started to write a whole bunch of automation. So this is classic automation, right? This is the traditional Chef, Puppet. We actually ended up switching to Ansible. And we ended up with these stacks that were easily reified, right? Just as part of our CI/CD pipeline, you would get this beautiful stack that would stand up, and all the traffic would migrate to it. It was really, really nice. And then we kept going, and then we went ahead and did auto scaling, right? So we were able to scale up and scale down our stacks. So it was a really, really nice job that our team did. So this picture is from the Workday talk from this morning. We stole that. But when I give this talk, I almost have some picture like that, which is you have your operators, and they're able to get this really nice view, and the automation stack gives you a lot of knobs and levers. Okay, so that's really, really, really good, right? So I think we should pat ourselves on the back as an industry that we've gotten to the point where now this is actually becoming feasible. But there are what I call post-automation world challenges as well. So yes, our automation stack gave us a lot of knobs and levers, but now we have a hard problem. We have to now go and turn those levers, and we have to figure out how to set those knobs and set those settings, right? So how do we do that? Like, how do we figure out how much of what resource is needed at what point in time for whatever goals that we have, right? So this is becoming actually a very, very interesting problem. So yes, we've created the ability to set these knobs. We've created this beautiful machine with lots of settings and knobs on it. But now we're sitting in front of it and we're like, well, what do we do with this? How do we set it up so that we can always achieve our QoS SLAs while minimizing cost, increasing performance, and so on, right? So this is the first challenge that I think hit us in my previous life. The next one actually caught me by surprise a little bit. So what happened is that we slowly realized that we're no longer running these legacy apps in our data infrastructure. And so we now have developers actually writing apps that are running in our environment. So now let's say for the sake of argument, you are a transportation company, and people go to your app and they order your transportation service, which shows up, and you're able to see when it arrives and so on, right? We have lots of examples of that. In fact, I took one Lyft ride and one Uber ride to get here today, right? So let's say you're providing the data infrastructure for that app. And so, of course, that's not where I worked. I'm just providing that as an example. Now, the developer writing the code for when my app powers on has to go and get my user profile, right? But that's really interesting. So the app knows me pretty intimately, and there's some amount of data that it keeps in my user profile. So as needs change, that user profile data changes. So for example, tomorrow somebody says, hey, I don't want to just track as part of this user profile, the last trip that you took. I also want to track the last 3 trips you took. All of a sudden, what happened is that the amount of data and the access pattern for that data that I may have optimized my infrastructure for beforehand, overnight, unbeknownst to me, changed. What did it change in this case? Well, okay, now there's more data to access. Maybe the access pattern changed, right? So now we're in this world where the data needs are changing constantly. So how do you provide resilience? How do you provide quality service? How do you provide SLAs in a world where you don't even know when the patch from a developer is going to go in and completely change what you thought was a nicely, cleanly optimized system? So this really caught us by surprise. The constant need to go and tweak our data infrastructure just out of left field, did not see it coming. Okay? Now, what's going to be happening and what's already starting to happen is that this particular problem is starting to get even worse, and hardware is helping make it worse in a good way. And that's in the sense that now we have more options and more layers, and the number of layers keeps increasing. So I've highlighted a couple of layers that are here now that we have to start thinking about now. How in our hybrid infrastructures, how in our data infrastructures that span multiple tiers, how do we make decisions about optimizing our applications when they're constantly changing? It's hard to predict the patterns, and then now we have to make even harder decisions about where to place, because the cost dynamics and the performance dynamics are becoming more and more complex. Okay, so I started out with a good picture, then we kind of went a little bleak. So the question is, what's the path forward, right? How do we go forward in our data infrastructures to be able to deal with this additional complexity, the more dynamic nature of the applications and so on? So what I've been dreaming up and then executing in this new enterprise, this new company, is kind of trying to answer this question, right? What if our data infrastructure was self-learning? Right? Could it just learn? When the developer changes and adds 3 more fields to a user profile, without even knowing that particular line of code changed somewhere, but just being able to see that there's a data access pattern change, could we just learn it in the data infrastructure and then optimize around it dynamically, immediately? So that's really an interesting area. And then the same thing goes to not just modeling the workload coming from the application. We're talking about infrastructure. Infrastructure looks up and down. So what about modeling the behavior of the devices that you're running on, the hardware that you're running on, the memories and the different tiers that you're running on, and the networks that you're going across? And if you could do that, maybe you can take the application model that you've learned and the infrastructure device hardware model that you've learned, match the two, okay, and have the pagers not go off as often. So that's maybe kind of the high-level vision that I think that whether what I'm going to talk about today as a solution works in your environment or not is less relevant to me, honestly. It's much more about, this is here. We have to do something about it. These problems are here, right? And in my career, I've come to the conclusion that the solution has to be something like this. It has to be something like this, right? So we'll see in the next few years where different ways emerge. What I'm going to be talking about with you is kind of the first attack at this problem. So to introduce the problem a little bit further, right? So today we have static data infrastructure. So in this complicated looking 3D plot, this point cloud, each dot, okay, represents a single application. So it could be a microservice, right? You're running maybe hundreds or thousands of microservices in your production environments. And each dot in that point cloud represents one application. But what it represents is the optimal parameters of the infrastructure to run that one application. So you can see for every application modeled here, the set of parameters are totally different, right? Does that make sense? I'll take questions as I go, by the way. So if thousands of different applications all have different operating points, and I'm only plotting 3 parameters here, right? You can see the complexity of the problem is getting worse with hardware and more hardware diversity and options available. Okay, so we know that applications have these dramatically different size and parameter settings, okay, as that are the optimal. So how do we do parameter setting today? How do we optimize our infrastructure or try to tweak it or try to, understand it? Well, today it's done by like running our systems in the default mode, right? Almost always. When's the last time you change the parameters of a cache? When's the last time that you change the parameters of any one of your database systems? I've asked this question in many talks, and very, very few people raise their hands. It's hard because it's complex, also because you don't know what you're doing. You're like feeling in a dark room trying to figure out, oh, what do I do? Tweak this, tweak that. What's going to happen? Could I affect my production or make it worse? So it's not that we haven't known that you can improve performance and that every application has a different optimal operating point. It's not that we don't know that. So this, we already intuitively know that there's a surface that's very different for each application. We just don't know how to, and it's too risky to try to do it. Try to actually make these changes in production. So instead, we just go with whatever. And so, of course, you rely on the open source developer that developed that particular application to have set the parameters in a reasonable way. So, of course, I then go and talk to these developers of these open source products that we all run in our infrastructures and say, hey, how did you set this? Well, the typical answer, it might not be a surprise to you, is that, well, I ran 2 or 3 micro benchmarks, and I found that the best settings were different for all of them. So I kind of just like picked the middle one that was not the worst for all of them. So that's how these things get set up today. So I'm just providing kind of examples and motivation for, static data infrastructures and what they leave on the floor. So at the end of the day, a lot of times when you're dealing with this sort of thing, you're obviously running non-optimally, but there's other problems as well, right? There is, if you cannot look underneath the surface and really model these behaviors, you end up with thrashing, you end up with pollution, you end up with unfairness between systems because they impact each other, and unpredictability. Okay, so I talked about this concept of, well, what if the data infrastructure is self-learning? Could that address some of these post-automation world challenges that we talked about? So I'd like to dive in to a particular component of the data infrastructure, that is caches, and talk about how we have found in our experience that the cache layer actually ends up providing a tremendous amount of control if you can learn and automatically figure out the workload as well as the hardware models. So first of all, caches are critical to every application, right? Caches, ever since the 1950s, have been critical to microprocessor performance, to operating system performance, because operating systems need buffer caches to be able to absorb wildly varied workloads. Okay. Same thing that goes with network systems, storage systems, anything that kind of looks like, hey, I want to compute on data, but my data is a little bit far away. You need a layer in the middle that's going to absorb the latency that's associated with getting data from far. So that's why microprocessors, like if you look at an X-ray diagram of X-ray picture of a microprocessor today, you'll see a square, and then you'll see a little piece of it that's the logic, and then everything around it, like 2/3, maybe 3/4 of the die area is occupied by caches, and the reason is the same. So, okay, caches are critical. Hopefully you buy that to every application and literally every system built today. My cell phone probably has like 30 or 40 different cache implementations running inside it at any time. But cache management has not really advanced since the 50s. So in terms of cache management, if you ask the question, well, how do you manage your caches today? Pretty much everybody says, hey, I monitor the hit rates or hit ratios, either one, right? And so it's an interesting question, right? We've had 60 years to work on this problem. Like, why is cache management just a single number to this day? And so it's actually even worse than that. So, caches may be critical, but intelligent cache management is basically non-existent. So why? Why do I make that bold claim? So let's go down and ask some questions that you would want to be able to ask of an intelligent management solution when it comes to caches. Here's an easy one. Is this performance good? So in this the black little window, I'm showing 65% as the hit ratio for an example application. Let me ask you the question. Because remember, that's the only data that you have for your cache. Is that performance good? Hard to tell. Maybe it should be 80%. Well, why? Why? Can that be improved? So if that was your workload, right? Hitting a cache, and you wanted to say, look, my latency needs are such that I want that to be at 75, 80, 90%. Can that performance be improved? How would you be able to, how would you do that, right? Anybody want to take a stab at how you try to improve the performance of that cache? Yeah? Right. Yeah, so the answer would be you have to recycle the contents of the cache, and usually the caches are doing their own recycling. So maybe what you say is, hey, Irfan, maybe you need to take that cache size, 128 gigabytes. It's clearly too small. Maybe you want to double it. So I'm seeing a lot of nodding heads. I want to double it. Well, how do you know that the performance is going to improve when you double it? Does anybody, I don't know, right? Of course you're going to say, of course it's workload dependent, but okay, fine, workload dependent, but even if you can observe the workload, how are you going to tell? If I go to 256 gigabytes, will that go to 66% or 90%? Or will it go to 60% or 40%? Could it go down? Could it get worse? Unclear. Okay, so how much cache do I need for application A versus B? What happens if I add or remove physical resources like DRAM? Yes. Yes. Yes, okay, so there we go. So let me repeat that for the recording and for everybody else. The example given was, well, maybe you start with your total data set. Okay, so maybe I've got, let's say 100 terabyte data set, and then you say, okay, heuristically, maybe 10% of it is what I need to have as a cache, and so that's exactly how people size it today, and so that's how you ended up with 65%. So my question is, did I accurately represent your answer? Okay. Got it. Yeah. Brilliant. Okay, so now so let me just repeat that. What you said was, Irfan, that think about it this way, right? So you start with maybe a 10%, right? And then you monitor and you say, okay, well, it's not quite hitting what I need to hit, so now I want to increase it or decrease it, and let me experiment dynamically over time using maybe some heuristics to try to adjust for it, right? So yeah, that's what people are doing today. But to be able to change production, you usually have to have a justification. You usually have to have some sort of an argument. And so that's what we're talking about, right? How do you justify, how do you figure out how to feed that heuristic that wants to increase the cache size, right? And what I'm saying is that today, you cannot answer that question based on the data that's available of how much to increase by in production. And that's very dangerous because it could drop. The performance could actually drop if you don't do it carefully. And so there are many, many, many more questions. Yes? Yes. Yes. Yes, that's right. So the. No, I'm not making the assumption. I'm saying that there's tiers of data. It's just tiers, right? So there's a fast tier, and then there's a crazy fast tier, right? So maybe SSD and DRAM could be, right? Or could be any combination thereof, right? Because usually, like, in the largest sense, right, you can't fit pretty much any data set in memory at large scale. So you have to pick. So there's different ways of picking. People either window the data and say only keep just yesterday, or they do a more dynamic scheme, which is, hey, I can't predict that sort of a window, so I'm going to do a cache, right? So I'm talking about the cache version of the problem. So there's a lot more questions here, but I think the answers are very similar, which is, hey, I cannot tell you what the answer is, Irfan, but if you give me enough time, I can tweak the system, I can play with it, I can increase, decrease, play with it, and hopefully by the time I get to the answer I need, hopefully the application has changed again, because if it has, then I got to do this over again. Fair? Yes? Okay. So I'm just going to translate that here and say, okay, if what you know is the 65% is your hit ratio, then if I just plot that out on the right-hand side as cache size on the x-axis, because really that was the parameter we were dealing with in this most recent example that we talked about, and latency on the y-axis. Okay, so then that 65% hit ratio may translate into that dot. That's what we have today. The reason why we can't answer any of the questions in my bold claim in the previous slide is because we don't know anything about what happens if we add more cache or remove more cache. And remember, this is just one of the parameters. There's actually many, many more parameters that you want to model on the system, just like any complicated system. I'm just picking cache size because that's the easiest one to visualize. So what if you could? Well, like, what if you could predict what happens if you could increase or move that dot, okay, to the right or to the left? What would happen, right? And so ultimately it comes down to that visualization. So what we want to do is we want to take the workload, we want to learn the performance model of that workload, right? Which is all about, like you were saying, it's about, and you were saying, it's about reuse, right? Because you want to recycle and you want to reuse, and that's really, really important because caching is all about reuse, right? If there was no reuse in a workload, then caching is actually useless. You should not spend any money on it, any effort or any energy in it, right? But most workloads have locality. So what you want to do is you want to learn the performance model, and the performance model is very simple from a mathematical expression point of view. It's just a function of the cache size in this case, and then other parameters if you wanted to get multidimensional. Okay, so what does that look like? Well, that looks like this curve. Okay, so now in this curve, and this is, by the way, a real production workload taken from an actual customer environment. And so now, yes, so we know where the dot is because we can measure that. That's the only point that we know today. But what if you could predictively know that if you were to add more cache or to remove any cache, what the impact of latency would be, right? If you could do that, I think that's the first step towards a self-learning data infrastructure, because now all of a sudden we can start to use that for a few interesting things. So let's talk about that. So imagine that your workload is running in that spot where the dot is right now, right? And so you, for example, gave this example of, hey, you know, what am I going to do if I want to improve my latency in that environment, right? I'm going to tweak and I'm going to experiment. Okay, so let's do that. Let's experiment. So let's say we are at that dot and we experiment and we double our DRAM, let's just say for this purpose, for the sake of argument, right? So let's say you're spending, you know, $1,000 a day on this big workload, okay? And now you're just spending $2,000 a day. Did performance improve? No, I'm seeing a lot of head shakes because performance didn't improve. Well, why? Because it's flat, right? Okay, so now our friend here, I don't mean to demonize you, but our friend here will say, okay, I'm going to keep tweaking. So now you go to 4x, now you're spending $4,000 a day. Right? In production, performance improve? No, did not. It cannot. 8x, now we're spending 8,000, which is 8x our cost. And I would give up by then. Maybe some of you will. Unbeknownst to us, every single megabyte of additional DRAM that you give to this workload will provide a commensurate benefit from that point on. So we understand why? Because for this workload, the working set, there's multiple working sets. Right? There's kind of like, think of it as like an hourly and a daily and a weekly working set. And so, of course, the longer the time period, the bigger the working set. Right? But there's a successively smaller periods that as soon as you fit them into the DRAM, you get this acceleration. Right? So is that clear? So this acceleration is coming from reuse, like you were saying. Right? But if you keep putting data into the cache, but by the time you need it, it's already evicted from the cache, you've got no benefit. That's where flatness comes from. So flatness is your enemy in these curves. These are just performance models. If you could build these performance models real time, now you can react to it real time, and you can size your environments, and as soon as that developer changes that user profile and adds 3 more trips to the profile, what will happen is this curve will change. You will see that the curve will change. You can go and size to it. So far, so good? Okay.
So if you can explain that, are you saying in this case, based on the workload, you're really going to change your memory runtime?
Yeah, so in this case, you do that, right? You could do that. You could allocate more memory to this workload versus another workload that doesn't need it, because you know for the other workload, it has a totally different set of requirements than you originally predicted based on your heuristics. And so you can remove from that workload, give to this workload, et cetera, right? So there's some contexts where that's easier to do, some contexts where you just bought 10,000 machines and that's memory is all you have, and we'll talk about how to deal with that situation in a couple of slides. There's lots of different things we can do. It's not always about buying or selling DRAM at long time periods. But so far I'm just focused on helping us understand what this thing actually is, what this performance model is, and what its power is if you could construct it. And today, that's not possible. Okay, so let's look at another example, right? So let's say you're operating at that cusp there. Okay, and if you look at that cusp, that's probably the worst operating point for that workload, because you paid so much and got no benefit out of it, right? So it's the worst operating point. So if you have this curve, one thing interesting that comes out of this performance model is you can just do basic arithmetic and find out, hey, give me the list of operating points that are efficient. And so you'll notice right away where the arrows are landing is always at the end of a cliff. Why is that? It's because you got, from an ROI perspective, from an efficiency, cash efficiency perspective, right, you got the biggest bang for the benefit. You want to hug the bottom. It's called the talus of the cliff. You want to hug the talus, right? Is that clear? Okay. So if you can find the operating points, you just want to hug those, and you want to go up in increments of those, right? You don't want to go up anything less than that size. Okay. What else can we do with it? Well, before I talk about some other examples, I wanted to show some diversity of these curves. So again, these are real production workloads using different cache algorithms and cache systems, and that's what the 3 different plots are. And the one I want to focus on is the green one. Actually, either the green or the red, you can see how even the different systems behave differently per workload. But what you'll see is, okay, let's look at, for example, let's look at T00. You see in the green, there's an example. As you added cache size, what happened? What sticks out as you think about that curve? Like, what's odd about that curve? Look at T00. The latency decreased and increased. So here's an example of a real production environment where if you were running that particular system, adding DRAM actually hurt you. So this is very dangerous to do in production. So just explore, you see, because things can get worse before they get better. It's because the cache algorithms are real-time algorithms, and they can only be so smart. So while trying to be smart, sometimes they make a mistake, and that mistake actually costs you in 10, 15% of cache hit ratios. And so this has been documented in academia for all the top algorithms. Now, of course, if you're using something like LRU, plain LRU, this may not be as big a deal because it's not a smart algorithm. So it tends to be much more monotonic. But these non-monotonics are present in pretty much every advanced cache algorithm. So that's one thing you can see here. The other thing is look at the diversity, right? There are workloads that go like flat forever and then have a single drop at the end. So for example, T08, right? You can feed it hundreds of gigabytes of DRAM, and only at 600 gigs will it get all the benefit, right? And whereas you'll see T18, it continues to benefit as you give it more. And then finally you have T05 where it gets all of its benefit right away, and then you can keep adding after that, no benefit. So now all of a sudden, given a fixed spend budget or already purchased hardware, now you have the ability to come in and say, hey, who gets what? Because I don't want to give T05 anything more than the 10 gigs that it needs, but for let's say T25, I want to give it maybe 15 gigs, and so on and so on and so forth. Right? So now you got that flexibility because you can predict what the performance result will be. Okay. So now what else can we do with this? So again, the goal is self-learning data infrastructure, right? So we looked at, okay, well, first thing we want to do is monitor it so you can size better, right? So what else can we do in this self-learning environment? So this is the same sort of curve, but instead of plotting just average latency or median latency, I've plotted 95th percentile latency. And to get to the 95th percentile latency in this model is just arithmetic, and I can offline show you. It's just like literally like 2 multiplies and an add, and you get the 95th percentile latency curve like this, right? Now, if you think about the 95th percentile latency curve against cache size, now something interesting can be done here, which caught me by surprise when we came across this. Okay, so you have latency on the y-axis. If you want to guarantee latency for your workload, now you have a predictive model that can let you do that. Does that make sense? Because all you have to do is to say, in this example, 7 milliseconds of 95th percentile latency. And it could be 99th, it doesn't matter here. It's just a matter of measuring the right latency to plug into the formula. But now you're able to come here and say, hey, to be able to guarantee this workload, 7 milliseconds latency, I now know how to do it. All I have to do is allocate enough cache, and I will be able to guarantee it. Do you buy that? It's a pretty interesting little subtle thing that when we finally came across it, it just blew our mind. And so how would you do it? Well, in this case, you would say, look, as long as the cache allocation is more than 16 gigabytes, you're guaranteed to get that latency by the math. Okay. Now, if I was you, I wouldn't set it at 16. I'd set it at like 18 or 20. Right? Because why? Because the workload that is being used to measure this curve in real time, that workload also could change it a little bit, right? It could have these curves are not static. They shift and they moan and they skew over the course of time. So to absorb that, you want to add some buffer in front of it. But if you were to give this workload 16 or 18, as long as the workload doesn't change, you're going to have 95th percentile latency of 10 milliseconds. So how's that going to happen? Well, the cache hits will be a certain high percentage, and the cache hit latency will be very low, and the cache miss latency will be high, and the average will work, or the 95th percentile will work out to this. Does that make sense? Okay, so we started with this very simple curve, and so far we've been able to do some pretty interesting things with it. Here's another thing, right? So this comes to one of the questions that was asked earlier, which is, okay, so what if I don't have enough DRAM, or I've not already purchased enough DRAM? Is it just about DRAM, or is it about different tiers and different layers in my system? So here's what I did, is took the same curve, and now instead of trying to model latency, what I'm trying to do is to figure out the combination of my latency SLAs that the application expects and my hardware resources, and say what percentage of this workload needs to run in tier 0 and tier 1 and tier 2 and tier 3 to give me the lowest cost way of getting my 95th percentile latency. And so for some workloads, you'll have lots of allocation of DRAM, okay, and little bits of the rest of it to fill it out, and everything else goes to, say SSD or whatever your slowest tier is. But for other workloads, it will be something like this in this example, which is you only need a little bit of that super expensive memory, because the SLA expectation of that application can be met without burning a lot of the most expensive resource. All we did was drew vertical lines and horizontal lines on this curve. That's all we've done. And interesting, things are coming out. Make sense so far? So now we can do other things. Now this is a little bit more mathematical. I won't go into it, but what I wanted to show at the high level is that any time that you had those flat regions, remember we had a long discussion about those flat regions and why they happen, because the working set is not fitting. And so by the time you need to reuse the data, it's already been evicted from the cache and you have a total waste. So it turns out that those are the worst workloads, for caches. But if you know this curve ahead of time, you can do some tricks inside your caches to actually eliminate them. And so the way that works is basically once you know that you're in a flat region, in other words, the memory that you can afford to give to this workload is such that it doesn't fit the working set. That once you know that, and this predictive model, which is this curve, lets you know that you can actually play some tricks so that you already know you're going to thrash most of the time. So you intelligently choose to thrash most of the time, but once in a while you don't thrash, and you can end up in these diagonals, these convex hulls of that curve, okay, in a provable, optimal way. And your worst workloads all of a sudden start to behave like the good ones. Okay. And so what we've seen examples of that, I'm not sure if I have examples here, but the examples of that have to, 50, 80%, sometimes 100% reductions in latency. And the way it works is that in any of these flat regions, you can pick to operate on any of the cache sizes, and instead of it being flat, it'll be the convex hull. So it requires some trickery, but as soon as you can do that, you get these benefits. Again, all we did was draw, in this case, instead of drawing horizontal lines and vertical lines, we just drew the diagonal lines on the curve, right? So it all comes down to the ability to be able to model these in real time. So here's some performance examples from that cliff reduction technique. Again, the cliff reduction technique only is going to provide you benefits for the super flat regions. And what's happening in the red region is a completely dynamic algorithm which is trying to operate the cache away from those flat regions. And so you can see the results in terms of reductions in cache sizes needed to provide the optimal performance of up to 3 examples. Okay. So self-optimizing data path is what we started off with, right? Because the argument I made is that the data infrastructure and the data path is becoming more dynamic because applications are changing more frequently, that the hardware is becoming more nuanced and having completely new tiers in the memory and the solid-state device hierarchy, okay? As well as the new challenges associated with a world in which the knobs are there. You can reify your stacks, your application stacks, even your software-defined storage and software-defined infrastructure stacks, right? But what are we going to do with those knobs to actually affect the SLAs that we expect and drive costs down, right? So we started off with that, and then I said, okay, well, to be able to do that and do it smartly, you need to do modeling. You need to be able to have some predictive model of how the system is going to work. The problem is that the data path and data infrastructure has been notoriously difficult to model, and we're now 60 plus years in the history of caches, in the history of, tiered data infrastructures, going back to about 1957, right? And we haven't been able to do that. So Cache Physics, my company, is the first company that figured out how to model these curves in real time and to embed them and make them so inexpensive to be able to compute that you can embed them inside any of your cache infrastructures. In fact, if microprocessor vendors would let us, you could actually put this inside the algorithm, the implementation of the algorithm inside of microprocessors. It's that cheap to be able to compute these curves. And so now we're working with customers to insert our software into their data infrastructure. And the first step for that is this monitoring step, right? To be able to visualize, just like the dashboard that I showed you earlier, for each of your applications, for your developers to be able to see what the profile of their workload is, for your operators to be able to see what the profile of the application that they're supporting is in this first step, which is monitoring. So monitoring is observability, which is clearly the first step towards anything that's self-optimizing. Right. Then there is the auto selection of dynamic parameters. So this is one of the slides that's in the deck. It's available to you. We can talk about it offline. I didn't go into the nitty-gritty details because I wanted to leave time for an open discussion. But in this picture, suffice it to say that all of the curves are the same workload. They're actually the same exact workload. So why are the curves different? Because we model different parameters. And so you can clearly see that using different parameters, right, depending upon what allocation you're giving to this application, that the optimal parameter is different, right? Because the curves look totally different, even though the workload is the same. We just modeled it with different policies. Then we talked about latency guarantees, and I think this is kind of the holy grail, right? Which is like, can I have an infrastructure that always is looking to see what resources I need to provide to hit the SLAs, and I have the confidence, okay, that it will increase resources just in time so that my SLAs are still met, but at all times obey the rule of don't spend more than you need to. Don't allocate more than you need to. Okay? Now, you don't do that normally, because normally you just come in and say, hey, give me like 4x what I think I need because I don't want to have an SLA violation. So because we don't have the confidence, we don't have the visibility, we don't have this X-ray machine that's going to tell us what we actually need. And so as soon as you have these performance models, right, we have the confidence to be able to go in and say, okay, we're going to allocate what we need, because as those needs change, we will know it and the system will automatically allocate. Okay, so this is a key thing in a self-optimizing data infrastructure. Accurate tiering we talked about as well, which is, does everything need to be completely in DRAM or completely in 3D XPoint or MRAM or PCM or those new tiers of memory that are becoming available? Or can we put some of it in other layers while still achieving the SLA, because now we're talking in the language of SLAs, and we're talking in the language of IOPS, or transactions per second, or QPI, or QPS, sorry, or milliseconds, right? Latency reduction, which is this secular technique, which takes the worst possible workloads that do the most amount of thrashing and secularly improves them, and all the other techniques provide optimizations on top of it. I'd love to get feedback on what to call that thing, because I struggle with it, because I can't say acceleration, because caches are accelerators, right? So this is accelerating the accelerator, so I don't know what to call it. Maybe accelerator squared, right? We need to come up with an actual marketing term for this. Because it's non-intuitive how to explain it. And then multi-tenant isolation. So as you go down the journey of this automation world and the microservices and the Dockers and the container and Kubernetes world, you end up sharing physical resources. There's just no way around it. And so if you're sharing a lot of resources, now you have multiple tenants. Now those tenants could be the same tenant, really. It's the same company. It could be your infrastructure that you purchase, but it's the microservices that are interfering with each other, right? So you want to be able to do some isolation. So how do you do that isolation? Again, these models provide you the ability to think that through. So the end result is, you're able to safely quantify the impact of changes that you're going to be able that you want to make. Get incredible cache efficiency improvements. For the first time in history, be able to actually hit latency SLAs while minimizing cost, because you know exactly what resources to provide to each workload. You can completely automate that. And as changes are happening, you're able to monitor and see why SLAs were no longer met, okay? And you can then subtract from that and figure out, hey, the actual application pattern changed, and that's one thing we cannot do today. We cannot make an argument as data infrastructure people to our developers and say, hey, the problem is you changed the app, so I didn't know you were going to change the app. Can you just tell me next time? Or put me in staging, or at least be able to understand, like, why is it that my caches and the remainder of my data infrastructure was not able to handle the load that I had seen before, and higher consolidation ratios and capacity planning. So you'll be able to take something like this and actually talk about, hey, if I increase my load 10x using the same pattern, what will happen? You can actually just completely do capacity planning. So cache systems have been, and data path infrastructure in general has been resistant to capacity planning, because of access patterns being not visualizable, but now they're visualizable. Okay, so I'll end with simply saying that here's my contact information, my co-founder and partners in the back also. So I would love to talk to you if there are further questions, or if there's any way that we can help. So we have, how many minutes do we have for questions? Okay, so we have maybe 7 or 8 minutes for questions. Go ahead. Yes.
So after this, we're talking about the data path prediction. Is there a kind of concept of the elastic cache, meaning you increase the cache to 64 GB or 30 GB because your needs are going up, but then there will be a time where the needs may go down.
Yes.
Instead of reducing
That's right.
cache.
Yes. Yes.
So basically, in a way, another way to look at it is like you put a auto in a cruise mode, as you're going up the slope, you have to pump more and reduce the gas and go down.
Right.
And is this model, can this model be extended for computing as well?
Okay. So let me repeat the question. So the first question was just checking to make sure that we're understanding correctly. So as the workload demands are going up, or the workload patterns are changing, that we're able to detect that. And if that means to hit the SLAs that were before, kind of like how cruise control, you set a miles per hour, and then sometimes you got to pump more gas to get to the same miles per hour, sometimes less, but you always want to get the miles per hour. If we're translating that into latency, this is going to let us understand, hey, to be able to hit that latency target, here are the cache resources you need, right, given your actual underlying database or persistent store or whatever, right? And then when fewer resources are needed to be able to hit that miles per hour or QPS or latency target, then now you can take your foot off the gas pedal, or the computer can take the foot off the gas pedal, the cruise computer, and still be able to hit that with fewer resources. So that was a double check, and the answer is yes, that's the idea. Now there's two contexts for that. One is elastic cache in the cloud sense, where you can actually like buy by the minute more or less DRAM. Okay, but there's an on-prem version of that, which is multi-tenancy, which is what does it take to hit SLAs for every application? Let's make sure we have that. Now everything, all the remaining DRAM we want to partition and provide to everybody, so we can even do better than our worst case SLA. So maybe my 95th percentile latency needs to be always 7 milliseconds. But if it's 5, I can delight my customers. Right? So 7, I'm going to allocate 4. I'm going to guarantee you that 7. But to be able to, if I can give you more, and that's my spare resources that I can move around, right, inside the same already purchased sunk cost data center, right, I can delight customers more. But I never want to miss SLAs, right? So in both contexts, either buying or releasing or renting memory, or in sunk cost data center, but just partitioning better, this applies. So the next question was, does this apply to CPU? The interesting thing is that CPUs, this problem is actually relatively easier because a megahertz is a megahertz. It's not quite true. Megahertz on one CPU might be 0.9 on another, but it's close enough, right? So if you ask somebody, hey, I'm going to double my load at Christmas compared to what it is now, and say, can you capacity plan for that? The person will say, oh yeah, I need twice the machines. But we know in the case of caches and the data infrastructure, the full data infrastructure, that's not the case. Doubling your workload doesn't mean that you can satisfy it by doubling your cache. Doubling your workload might mean 10 times the cache, or it might mean the same amount of cache, right? And so the problem was not solvable using the traditional auto-scaling software that is used in CPU. This problem wasn't solvable there because it's a much harder problem. And that's why it's taken this long. That's why we're the first company that's kind of figured this out. Yeah, go ahead. So we do work with vendors who want to take our IP and put it inside their SSD or put it inside their controllers. Okay, we do that, but that's not our primary business model. We'll do it because it's interesting and it's fun and it's a low overhead sort of way of doing business. But that's not our core. Our core business model is working with customers who are deploying caching systems, in-memory computing systems, hybrid systems, right? Hybrid meaning DRAM, SSD, disk, and other layers, fast SSD, slow SSD systems. And they have these very, very hardcore challenges about, I have these thousands of microservices. How do I decide who to give what to? And by the way, that changes every few hours because let's say you're running an ad tech. One of our customers is running ad tech. And they have these ridiculously large farms of servers. And each server is serving a portion of the overall global ad space. They cannot predict which server is going to be hot because they cannot predict which ad is going to be hot because they cannot predict what the world is going to do and the internet's going to do in the next hour. And so they have to be in this mode where they're constantly like adapting their infrastructure to be able to handle the load, because if they try to do, let's say, a terabyte of DRAM for every server, there's not enough money in the company to be able to buy that much infrastructure. They just cannot. They have to have pools that they lease out. They don't know how to do it. And so that's an example of what I'm talking about here. So that's the sweet spot for us, working with customers running caching or tiered caches or tiered systems, right, that need SLAs. Did that answer your question? Yes.
Yeah. So one of the use cases we have is, I'm not sure what you were there, but I guess talking about IoT, right? So we have this different SLA on trading money versus trading idea.
Yeah.
So we were thinking to really basically keep all 1 year data within memory always.
Yes.
And then data beyond 1 year is beyond SSD, right? So, but if somebody obviously requests, then we have to bring that into the process.
Yes.
So I guess I'm just trying to understand where you can help. Is it you can monitor our workload and be able to optimize it and suggest the best configuration for the environment, or I guess if you can really shed light on that.
Absolutely. So the question was that in this particular example of an environment, there's kind of two kind of business sort of reasons, business SLAs, right? For 1 year history, there's a very specific requirements, and so the idea was to put it into DRAM, DRAM only sort of thing. But for the 5-year trading data, well, maybe that could be resident in SSD and then pulled up into DRAM as requested and so on, right? So I think my encouragement is to think about this as what is the SLA that you want? So if the SLA for DRAM is, for every request, I will have 10 microseconds to respond. Okay, that clearly needs to be DRAM. And in fact, we should be talking about like really big LLCs and L2 caches inside the processor. Okay, that to be able to achieve that level, right? But if for even the 1 year data, if your requirement was, let's say, a millisecond, well, maybe by looking at the patterns of this workload, you can decide, hey, I want to be 90% DRAM and 10% or 50-50 because I can, even at the 99th percentile, I can still hit my budget, my latency budget, while having my cost, right? Those are questions that cannot be answered today unless you do modeling like this, right? So that would be the first step is, let's study the workload, let's figure out what the patterns are. So I'd like to finish here. I'm available for the rest of the day. Vikas is as well. Would love to be able to talk to you and exchange notes and ideas. Again, just we're at that stage where even hearing about a specific use case for your team would be super helpful. Thank you so much.